Welcome back, and a big warm welcome to Joyee Cheung. Um, Based in Zhengzhou in China, Joy has been involved with Node.js since 2016. She is a member of the Node.js Technical Steering Committee and a V8 committer. She works on the compilers team at Igalia. Today, she's going to give us an insight into how Node.js spends its time in starting up from scratch and to look at recent changes in the Node.js codebase that have improved the starter performance. So please welcome Joyee Cheung and Node.js startup performance.
Hi, um, I'm Joyee. Thank you for having me here. In this talk, we're going to take a look at the startup performance of Node, uh, how it evolved, and how we got this far. So, a little bit about myself. I am Joyee. I work on the compilers team at Igalia. I am on the Node Technical Steering Committee, and I'm also a VA committer. In the past year, I have been working on the Startup Performance Initiative in Node. You can find me on GitHub or Twitter via the handle Joyee Cheung. So enough about me. Let's talk about Node. So there had been quite a few issues about the startup performance in Node Core. Take this one, for example. This was opened before we released our recent optimizations of the startup. It used to take around 60 milliseconds to start up Node on a modern Skylake server. So after some refactoring was done and one of the optimization landed, which we are going to talk about in detail later, the startup time on the same server dropped to 21 milliseconds. So the startup was reduced by more than half. Oh, okay. So here is an overview of benchmark results from 3 versions of Node. 10, 14, and 15. This shows the startup time of these binaries in milliseconds. The first group measures the time used to load an empty script, and the second group measures the time used to load a set of public built-in modules shared by all these 3 versions. The numbers are a bit different from the ones described in the previous issue because this comes from the Coffee Lake CPUs, but as you can see, from 10 to 15, we've reduced the load time by around 40 to 50% in both benchmarks. So how did we get this far? This was achieved mainly by using these 3 tricks: refactoring to avoid unnecessary work as startup, implementing code caching, and integrating the VA startup snapshot. So to understand how we use these tricks to improve the startup performance, let's take a look at the Node startup process. So this is an overview of the Node Bootstrap. When you type Node from the command line, here are the things that Node is going to do before it can execute your code. So first, we need to do a few setups that should only be done once per process. This includes processing command line flags, setting up signal handlers, initializing the thread pool, and creating the default event loop, and so on. And later, the process is initialized, and one default event loop is created. Then we move on to set up a VA isolate. For people who aren't familiar with the embedded interface of the VA JavaScript engine, VA isolates are the instances of the VA engine. It encapsulates, for example, a JavaScript heap, a microtask queue, pending exceptions, and so on. In Node, the main instance has one VA isolate to execute JavaScript. And if in the process there are workers created using the worker thread module, each of them gets their own VA isolate. So the process and the VA isolate are initialized from the C++ layer. After that, we are ready to execute some built-in JavaScript. For your information, about half of the Node core is written in JavaScript. To use JavaScript for further bootstrapping, we'll need to initialize a VA context. So what is a VA context? A VA context is a sandboxed execution context that encapsulates JavaScript built-ins, also called primordials, including global this, array, object, and others. When you call vm.create context from the userland, this is what the return result includes. It is a new context with a different set of built-ins. In Node, userland JavaScript is executed in the main VA by context by default, sharing the same context as the one used by the built-ins of Node. To avoid being affected by user modifications of these JavaScript built-ins, we copy the original ones at the beginning of the startup so that the built-in modules of Node always gets to use the authentic JavaScript built-ins. So this is the kind of work that we have to do during the startup. Now we have a V context ready for JavaScript execution. Next, we are going to initialize the JavaScript Node.js environment. To initialize the environment, we first initialize the components that are independent of runtime states. This includes initializing the internal module loader that we use to load one built-in module from another, and most of the globals, including the process object and its properties, buffer, set timeout, clear timeout, most of the web APIs that Node implements, and so on. This is done primarily by running JavaScript, since the internal module loader and the globals are mostly implemented in JavaScript. Okay. Sorry. So after the runtime independent components are initialized, we then move on to initialize the event loop so that we can process the timers and the immediates properly later. Then we'll initialize the VA inspector. We can only start debugging JavaScript, internal or not, after the VA inspector is initialized. And then we initialize the runtime dependent states. During this phase, we configured the environment according to the command line flags and the environment variables that the environment gets. And most of the setup is optional depending on how the environment is configured. We call this phase pre-execution. For example, this is what the initialization of no warnings look like. If the user asks no, not to write warnings to STD error, we don't install the warning listener that does this. If the user does not configure no to stop doing this, we'll install the listener. After the pre-execution is done, the node environment is ready and we can start the execution. We'll select a main script to execute JavaScript. Which script gets chosen depends on how the process is started. For example, if the user passes a file name to Node from the command line as the entry point, we'll load a main script that detects the type of the entry point and loads it with either the CommonJS module loader or the ES module loader. If the instance launched is a worker instance, we'll load a different main script that set up various listeners on the message port and start listening. When the worker thread receives the script from the port, it will compile it and start execution from there. And after the main script is run, we will kick off the event loop and run this until nothing keeps it open. Library thread pool will be created if any asynchronous file system operation is used. Okay, now we've looked into the startup process. Let's see how we use these three tricks in some phases to reduce the startup time. First, refactoring. This is pretty straightforward. For example, a lot of built-in modules depend on each other, so we can lazy load built-ins that are not always used. The downside of doing this is that we will spend more time loading these modules when the user invokes some operation that really requires them. So this was just a temporary thing. We can revert the lazy loading when we can just deserialize them from the startup snapshot, which we're going to talk about later. Another thing that we can do is to avoid unnecessary work like creating the console, which may be a TTY string or a file string, depending on how the process is started. The time we spend on this can be saved using the startup snapshot because, for example, you can snapshot a file handle. So all of this must be done at runtime anyway. Um, so another upside of refactoring is before it was done, we didn't really have that separation between runtime dependent initialization and runtime independent initialization. These were all intertwined, which made it difficult to integrate the startup snapshot, which needs a state that is runtime independent. So after the refactoring, we have a clean break between these two phases, and we've shrunk each of them a bit. And then there's another trick called caching. As you can see, during the startup, there are a lot of JavaScript that we need to execute. Previously, these all need to be compiled from scratch when you start a node process. And the compilation took a significant amount of time. During 14, we integrated vehicle cache to speed up the compilation of internal JavaScript modules. Before the integration, we needed to parse and compile the source code of these modules at runtime before executing them to create built-in modules. After the integration, we compile them at build time and serialize the compilation data, which is embedded into the executable. The compilation data contains the bytecode generated from the source code, and with this, the next time we want to execute the same source code, VA can skip a lot of the parsing and compilation process. So at runtime, we can directly deserialize the compilation data from the executable and use them to speed up the compilation of these internal modules. And the third trick that we can do is to integrate the VA startup snapshot into Node. For this, we need the runtime independent state that we can take a snapshot from. As explained earlier, this was done by refactoring and splitting the environment initialization process into two separate phases. After the refactoring, we essentially look at the runtime independent initialization of the context as a whole. We would take a snapshot from the context after these are done at build time, and load the snapshot at runtime. Before we integrated VA startup snapshot into Node, we had to run a few scripts in order to initialize the primordials and the globals, including the process object and its properties, and also the buffer constructor and all kinds of web APIs that Node implements. So these scripts would in turn load a bunch of internal modules to complete the setup, and this took time. Now we run the scripts at build time and serialize the internal context into a blob that gets embedded into the node executable. Then at runtime, instead of executing the scripts, we directly deserialize the result of the previous execution into a class, which speeds up the startup. This was the CPU profile of the startup process before the startup snapshot was integrated into Node. So at phase one, we initialized the internal module loader for the internal modules to load each other. At phase two, we initialized the globals. At phase three, we performed the pre-execution and load the user script. After the startup snapshot was integrated, we no longer need to perform phase one or two anymore. At the beginning of the startup, we'll just deserialize the snapshot taken after the first two phases are completed, which is the gray box on the left. As you can see, this saves us quite some time. So during this journey, we not only improved Node, but also contributed to VA by finding and fixing bugs in the startup snapshot feature. For example, during Node 8, we once disabled the default VA startup snapshot for pure JavaScript built-ins because the hash seed was fixed after the built-ins were deserialized from the context. And this introduced a vulnerability that attackers can use to perform a denial of service attack. You can read more about this in the VA blog post linked here. The solution to this was to generate a new hash seed and rehash all the JavaScript objects deserialized from the snapshot. And this was shipped in Node 8. So this worked fine for a while until we started to customize our own snapshot. And we found out that the rehashing of maps and sets were not supported. This was understandable because VA does not use maps or sets when it creates its own default snapshot. So we went ahead and implemented the rehashing so that we can use these language features in our own snapshot. Another thing that we've been working on is supporting class field initializers in the VA snapshot. As a stage 3 feature, this was once used in our event target implementation, but we later reverted back to using symbols. So one of the reasons was that the class field initializers were not supported in the snapshot. And another was that the initializers are not yet optimized, so they are kind of slowed. You can read more about this in the Nearform article linked here. So, After we discovered this bug, we are currently working on the support of class field initializers in the VA startup snapshot. So on the on the side note, we at Igalia also plan to work on the performance optimization of the class fields and parameters sponsored by Bloomberg, so that people can use these language features without worrying about the support issues. Apart from language feature support, we are also planning to provide user-line snapshots in the future. For example, the users may take a snapshot of an application and write it to disk. Then they could either load this snapshot blob from the file system or build it into an executable to speed up the startup of their own applications. This feature may be provided using command line flags or APIs under the worker thread module or the child process module. To follow our work, you can check out this issue in the link. So finally, I want to thank Igalia and Bloomberg for supporting my work, and special thanks to Anna Hennison for her help on the technical side of this project. Thank you for listening.
That was great. Thank you ever so much, Joy. I've got a couple of questions for you, but just to remind people, if you've got any questions that you would like me to put to Joy, could you put them in the Q&A tab on Slido? So, Joy, what is inside the startup snapshot?
Okay, there are two types of startup snapshots. One is the isolate snapshot, which contains like objects that are shared across the VA heap, for example, strings and numbers. Another one is context snapshot, which contains non-primitive JavaScript objects in the heap, like the JavaScript objects that you create. Um, yeah.
Thank you. Thank you. Okay, so what are the runtime dependent states that you mentioned in your talk?
So the runtime dependent states include states that are configured with command line flags or environment variables. For example, the process dot uh, argv array and the process dot env object. Like obviously, this would be different when you start Node in different ways. So can be included in the snapshot and have to be initialized after we dehydrate node from the snapshot.
Okay, thank you. So we've got a question here from Nukta, I think. What is the absolute minimum startup time that you think can be reached theoretically, as in sort of napkin math? It doesn't have to be exact, but what do you think could happen?
I think it might be possible to reduce the startup to around 10 milliseconds. I've checked before, like the startup time of Lua and the startup time of Pearl is around 6 to 8 milliseconds on my laptop. Right now, Node is like around 20 milliseconds. So I think there is still room for improvement. But there are a lot of refactoring and like some kind of ICU lazy loading that we need to do on the VA side to make this happen.
Mm. Oh, yeah, okay. Thank you. I've got it's kind of a comment from Michael Dawson, but looks like the work improved the startup. Did it also decrease the binary size?
I haven't checked actually, but I think it should like increase the binary for like with around like by 1 or 2 megabytes probably. The code cache is not that big, and the snapshot is actually smaller. But like as we implement the userland snapshot, this might be bigger depending on how big the heap of the user application is.
Great. Well, thank you ever so much, Joyee. And it was a great talk. Thank you. And if you've got any more questions, you're on Twitter, aren't you?
Yes.
Brilliant. So you can get in
Yeah.
touch there.